Hi, welcome to the Stat 110 Midterm 2017 Solve. This is problem 4 of this midterm. As for the last few problems, I first encourage you guys to solve these problems on your own first, and then get emotionally attached to the problem, and then come back, look at the solutions on paper, or look at the solutions as I solve them here. So this is problem 4. This is a normal distribution question. And let's get started. So the first part asks you to find the expression for this expectation as an integral, do not simplify. So we're probably going to be using some sort of definition of an expectation because it's an integral and this is a continuous distribution. So we see that this like z squared phi z thing, we're looking for that expectation. And we have a good friend named Lotus, which will tell us the expectation of a function of, say, z in this case, is equal to the integral of the function of z, little z, times the, I guess f was a bad choice, let's use g, times the CDF, f, big Z, of little z, dz, over the support of z. So let's say negative infinity to infinity. So that's what Lotus tells us. So in this case, our g of z is equal to z squared times big phi, the CDF, of little z. So by Lotus, our expectation, big Z squared phi big Z, is going to be equal to, let me find some more room. Let me make Lotus a little smaller. This is something we would have on our cheat sheet if that was a thing this year. So we have, this is going to be equal to the integral of little z times big phi of little z, since that is our function with little z plugged in, times the PDF, which is this guy, the PDF of a normal, and this is z, a standard normal. So z is standard normal. So the PDF of that, you can look it up on your cheat sheet, but it's 1 over square root 2 pi e to the negative z squared over 2. And this is all dz. And the support of a normal is negative infinity to infinity. So this is going to be our Lotusified expectation. We have the function with little z plugged in, the PDF of a normal, all integrated. So this is just Lotus. All right, so that's part A. Let's do part B. We're looking for the probability of big phi of z is less than 2/3 and simplify. So we can't just leave this one as an integral. So here's one way we can do it. So probability of phi z less than 2/3. And if I recall, I think this is how I did it when I took this midterm back in the day. We can just take the functions, like take inverses of both sides and it's still equivalent. So probability of phi inverse, big phi z, is less than big phi inverse 2/3. And then this is just going to be probability of big Z is less than phi inverse of 2/3. And Z, again, is standard normal. So this is actually just a definition of the CDF. So this is going to be equal to big phi, the CDF, of this value. So phi inverse, 2/3, and CDFs are invertible functions, so this is going to be exactly 2/3. So this is one way you can do it. This is sort of the like will work for any CDF kind of thing. But another way we can do it is to use my iPad. Universality of the uniform, which is like always a very cool thing, but maybe sometimes a little harder to wrap your head around. So universality of the uniform states that, let's say we have a random variable x and its CDF, f sub x, and this is U, a uniform. U distributed unif 0, 1. Then universality of the uniform says that fx of x is distributed as uniform. And if you like took the inverses of both sides here, you would see that x is distributed as f inverse x uniform. So this is what universality of the uniform tells you. So if we look at what we're dealing with here, so I'll make this a little smaller. We're looking at phi z, and phi is the CDF, and phi is the CDF of z. So plugging in phi z, that should be distributed uniformly. So we have that phi z is distributed unif 0, 1 by universality of the uniform. So that means we could just say probability phi z less than 2/3. That's going to be equal to probability. I'll just do this for notation's sake. I like U's for uniforms. And from here, you can see that that's just going to be, if we look at the stick, this is 2/3. We want our U to be less than 2/3, so that's just 2/3 of the stick. So this is going to be equal to 2/3 itself. So that's the same answer we got before here, just found in a different way by universality of the uniform. So that's part B. Now for part C, find probability x is less than y is less than z. So if we recall x, y, and z, these are IID normals, standard normals. Let me just check that. Yep, so they are IID standard normals. So we're looking for, like, I guess note for like continuous random variables, like the probability x equals y, this is going to be 0 because it's just like, it happens like kind of like for any continuous random variable, the probability is any particular value is going to be 0. And this is essentially being like big X is equal to X and Y is also equal to little x. These are both probability 0 events. So we don't really have to deal with those like less than or equal to sign kind of things there. So this problem becomes a problem kind of symmetry. So all of these values are just IID. So I claim that like if we were to just toss these guys on the infinite number line, not a finite number line, like we would have X, Y, Z. But with equal probability, we could have just had Z, Y, X or X, Z, Y. And all of these are going to have the same probability of happening, just like via their PDF values at each one of these points kind of thing. Like it's just the same set of points. So the like extremity part of the normal distribution is taken care of, but it's now up to just the labeling of these random variables. They're IIDs, so we can just switch the labels around as we please. So I claim that all the orderings of X, Y, and Z are equally likely. Like we could have gotten this, but equally likely we could have gotten this. And it's just up to like when we're tossing the random variables onto the number line, like which order do they land in. So that means like let's consider how many possible orderings we do have of X, Y, and Z. So we have 3 variables, so that's 3 factorial orderings. This is 6, and X, Y, Z is just one of the 6 orderings. So this is actually going to be our answer. So it's 1/6 by symmetry. So yeah, that's it for problem 4 of this midterm, and that's it for the entire midterm. So hope you enjoyed this mini series of me live solving the midterm questions. And as always, you can always feel free to reach out to me for Slack if you have any questions dealing with the midterm or the class in general. Good luck studying.